Hello, in this video I'm going to be talking about titrations. We'll go over the basics of acid-base, the different types of titrations, how to interpret and make calculations along a titration curve, what buffers are, and finally, the steps to tackle titration problems. So what are titrations? They're a way to determine the concentration of the analyte, which is down here, using the volume of titrant, which is up here, required to reach the reaction endpoint. The analyte in the beaker has known volume but unknown concentration, and the titrant in the burette has known concentration and known volume, since we can control the volume that we drip into the analyte. When we talk about titration curves, note that the endpoint of this reaction is the equivalence point on the curve. We know when the endpoint happens by adding an indicator into the analyte, which changes color when the reaction is complete. Find an indicator with a pKa as close to the pH of the equivalence point as possible. In other words, the best indicators change color at the same pH as the endpoint. For titration problems, the M1V1M2V2 dilution equation, as you may know it, is very important. M stands for molarity to measure concentration, and V stands for volume in liters. The mole ratios are usually 1:1, but if not, look at the equation stoichiometry and determine what number you need to put here for N on each side. Ultimately, you're comparing moles to moles. There are many different types of titrations, but we'll be focusing on acid-base since it's such a big unit in AP Chem and the most common one you'll see out there. When you look at a burette, you should read it downwards, because the volume value actually increases as you go down. So this would be 14.00, 14.10, 14.20, and so on. Remember to always keep one decimal place more than the markings, so 14.3 would actually be 14.30. Since the markings go to the tenths place, you should record the volume to the hundredths place. The burette is labeled backwards, so when you do final reading minus initial reading, you get a positive value for the volume dispensed. Lastly, remember to read from the bottom of the meniscus when you're at eye level. Before we can talk about titrations, we need to understand acid-base basics. According to the Bronsted-Lowry definition, acids donate protons and bases accept protons. A proton is basically an H+ ion because a hydrogen atom without an electron is just a proton. When an acid gives away its proton, it becomes its own conjugate base, and when a base accepts a proton, it becomes its own conjugate acid. The K expressions over here are just equilibrium. So products over reactants, and since all species are aqueous except for H2O, which is a liquid, we don't see H2O appearing in the equilibrium expressions. H2O can act both as a base, which is a proton acceptor, or an acid, which is a proton giver. Because it has a special quality, we can call it amphiprotic or amphoteric. Here are some equations you should know by heart. This portion is directly taken off the AP Chem equation sheet. We already went over Ka and Kb, so we're going to go over the K value for water. The Kw equation comes directly from the autoionization of water equation, demonstrating water's amphoteric ability. Water is neutral. All this means is that the concentration of H+ ions equals the concentration of OH- ions. Specifically, at standard conditions at 25 degrees Celsius, the K value for water is 1.0 times 10 to the negative 14. To find H+ or OH concentration, square root the Kw value. Most times, water has a neutral pH of 7, but this can change as Kw changes with temperature. Kw is also a way to transition between Ka and Kb of conjugate acid-base pairs. This works because adding an acid equation and its basis equation gives the water equation, and when you multiply the K values, you get Kw. Next, whenever you see P of something, whether it be H+, OH, or the K values, just know that P means taking the negative log of something. This is the Henderson-Hasselbalch equation. It's derived from the Ka equation, and it's also a shortcut because you can directly plug in pKa or pH. So what's really going on? Acid-base titrations involve neutralization reactions where an acid and a base react to form H2O and a salt. Here's some examples. Moles of acid reacts with moles of base to reach the equivalence point. Monoprotic acids, which have the formula HA, have one equivalence point. These are all examples of monoprotic acids. The shape of the titration curve would be similar to this. Diprotic acids have the formula H2A, and since they have 2 moles of H plus per mole of acid, it needs twice as many moles of base to titrate the acid twice. So it would have 2 equivalence points. This is what this titration curve for a diprotic acid would look like. For this titration, we're adding strong base to the diprotic acid, so obviously the pH increases as the titration proceeds. And lastly, triprotic acids have 3 moles of H plus per mole of acid, and it has the formula H3A, and it would have 3 equivalence points, and so on. This is so important that it has its own slide. So at the equivalence point, assuming it's a monoprotic titration, for example, the moles of H consumed will equal the moles of OH added. Titration matches moles with moles. It's stoichiometry. All moles of acid reacts with all moles of base to reach the equivalence point, or the reaction endpoint, in their appropriate ratio. A strong acid does not need more base to titrate it. So for example, a weak 0.1 molar 1 liter acid and a strong 0.1 molar 1 liter acid will both need the same amount of base. Moles will always be moles. Use this equation right here to get between molarity, moles, and volume. Although volume should be in liters, you'll be given almost all titration volumes in milliliters. This is okay as long as you use milliliters on both sides of the equation. Remember that molarity times milliliters is millimoles, and molarity can only be moles over liters. However, acid-base strength does matter when we're talking about which type of titration we're doing and how it affects the shape of the titration curve. You should memorize these strong acids. Looking at the acid titration, strong acids completely dissociate, so they have a large Ka value, much greater than 1. This means that 1 molar of HCl solution produces 1 molar H plus solution. The pH of a strong acid will be based on its corresponding molarity of H plus. We can disregard the A minus or conjugate base because it is very weak and doesn't even act as base. It doesn't raise the pH at all. Strong bases are made of OH and an alkali or alkaline earth metal in group 1 or 2. Strong bases also completely dissociate in water, resulting in a large Kb value. We can measure the concentration of OH produced by the moles of OH in the original strong base. So 1 molar NaOH produces 1 molar OH minus, and 1 molar CaOH2 produces 2 molars of OH. The conjugate acid is also very weak because there is no effect on the pH. Everything else can be considered weak, which means that they have much smaller K values and much less or even negligible dissociation. Expect a weak acid or base to have the same amount of strength as its conjugate. For example, HF is a weak acid, so F-, which is its conjugate base, will still raise the pH of a solution. NH3 is a weak base, so NH4, its conjugate acid, will lower the pH. Remember that the P of anything basically takes the negative log of it, so a higher H plus concentration will mean lower pH, and a higher OH minus concentration means higher pH or lower pOH. So now we're going to go into the types of acid-base titrations. The first type of acid-base titration is strong-strong. An example is with HCl and NaOH. Taking the net ionic equation, which is only the species that reacts, we get this. At the half equivalence point, half the HCl has reacted with OH from NaOH, so the same amount of HCl and the Cl-, which is its conjugate base, is in the solution. Since Cl- is very weak because it's the conjugate base of a strong acid, it doesn't even affect the pH, so we can determine the pH at this moment at the half equivalence point through H plus ions from HCl. At the equivalence point, basically all the HCl has reacted with OH-, and now there are only the products H2O and the Cl-, none of which affect the pH. As standard conditions, the pH at the equivalence point is neutral, which is 7. When analyzing the curve, always think about what is in the solution at each point in time, how their concentrations compare, and how it affects the pH. Think about how a strong base titrated by a strong acid would look. The equivalence point would still be at pH 7, but the curve would basically just be backwards. What if we wanted to titrate a weak acid with a strong base? Well, again, we have the neutralization reaction right here, and an example would be acetic acid titrated with, say, NaOH. At the half equivalence point, the concentration of acid equals the concentration of its conjugate base. pH equals the pKa because when we plug this into the Ka expression, the two species cancel, and when we plug it into the Henderson-Hasselbalch equation, it becomes 1. Ultimately, you get pKa equals pH. This is an ideal buffer because there is an equimolar weak conjugate acid-base pair to react with any strong acid or base added so that the pH doesn't change too much. At the equivalence point, pretty much only conjugate base is left. The conjugate base of a weak acid has basic properties and it raises the pH, so the pH is actually greater than 7. To find the H+ concentration for the pH, use the Kb equation of the weak conjugate base and plug stuff in. To find the pH at any other point in time on the titration curve, you can plug in to the Ka the appropriate concentrations. You can also titrate a weak base with a strong acid. The equation looks a bit different this time, but the base and the H+ makes its conjugate acid and H2O. At the half equivalence point, half of the base reacts, so the concentration of weak base equals the concentration of its weak conjugate acid. Here, the POH equals the pKb. The amount of conjugate acid increases until the equivalence point, where there is almost only the conjugate acid left. Since the weak conjugate acid lowers the pH, it will be lower than 7 at the equivalence point. To find the exact pH, we can divide Kw by Kb to calculate Ka of this conjugate acid, and use the Ka to calculate the pH. But what if the pH is not equal to the pKa? Here's what we can do to get there. This conjugate acid-base pair ratio determines the pH range and changes pH from pKa. So when you're trying to reach a target pH from a different pKa, use this ratio to get there. You can use this equation for both POH and pH, so literally just plug stuff in. And for an ideal buffer, the pKa equals the pH. Perfect. Here's some buffer stuff that we won't really get into, but just remember this ratio determines if you will go up from the pKa or down from the pKa to get to the pH you want. Some main takeaways for titration problems in general. Number 1, adding a solution increases the total volume. This means that when you add in the strong base, when you're getting to the equivalence point, the volume changes, it increases. Total volume times the molarity of each species equals the moles. Using the moles, use a before change after chart to find moles of each species after the reaction is complete. What is consumed, what is produced, and what is left in excess. Using the moles, divide the moles by the total volume to find the new molarities of each species. Now think about what's in the solution and how does that affect the pH. If we're dealing with weak acids or bases, use the icebox and use Ka or Kb to find the H+ concentration or the OH concentration. Ultimately, you're finding pH. If you're dealing with strong acids or bases, use the H+ or OH- that you get directly from the strong acid or base to find the pH. And that is the end of our video. Thanks for watching.